Right, so here I am for homework 5, part A. And so in this part, I will be explaining why the substitution S equals J omega will give the long-term frequency response for a transfer function when given a sinusoidal input. So we'll have our transfer function, our loop here just summed up as G, and then our sinusoidal input, A omega over S squared plus omega squared. This is going to equal, the G is going to be some AI over plus S plus BI, just a bunch of those added up, times, plus E plus Fj over S plus J omega plus E minus Fj over S plus J omega. S minus J omega. Right, so now we can go ahead and simplify this. So we'll have multiplying by S minus J omega on the left side, we'll have Se plus Sfj minus J omega E plus F omega plus Se minus Sfj plus J omega E plus F omega over S squared plus Sj omega minus Sj omega minus omega squared. We can see we have a bunch of canceling out, and that becomes 2Se plus 2F omega over S squared plus omega squared. Now what I'm going to do is I'm just going to say that the value C equals 2E and the value D equals 2F omega. And I will explain shortly why I'm leaving that D with the omega in it. So then over here we have CS plus D over S squared plus omega squared. Right? And so now what we can do is multiply by S squared plus omega squared across. So then that goes into here. Right? And we'll see that the S squared plus omega squared, when we substitute S equals J omega, that becomes negative omega squared plus omega squared. So that cancels out. So we have GA omega equals CJ omega plus D. Now dividing by A omega, the transfer function at J omega equals CJ over A plus D over A omega. So now we can break this up into an imaginary and a real part. So I equals C over A, and R equals D over A omega. So this is just IJ plus R. Now I want to go back to this CS plus C over omega squared. This can, of course, be broken up into CS over S squared plus omega squared and D over S squared plus omega squared. So this first part here will be, when we do the inverse Laplace transform, will be C cosine of omega t. Then we will add on D over omega sine of omega t. Now we have our imaginary and our real. So C, rearranging that, equals A times I, and then D over omega equals A times R. Now what we can do is first take out the A, but also we can set this imaginary to be equal to some magnitude times the sine of phi. And the real is some magnitude times the cosine of phi. And that is just dealing with the complex plane, right? So your x-axis is real, your y-axis is imaginary. Right? So now to clean some of this up, right? Substitute this in. So we get, first, if we, first what I want to show is just like this I squared plus r squared equals m squared plus sine phi, or times sine phi squared plus cosine phi squared, right, which of course is 1. So I squared plus r squared equals m squared. So m equals the square root of I squared plus r squared. And then we can also look at the phi value. First, I'm going to rearrange so that I get a little more space on that side. So we'll have a, and then substituting this in, we'll have m and cosine of omega t sine of phi plus sine omega t cosine of phi. Right, now I can reset. So if we take I over r, let me get a better spot. We'll just do it in the corner here. I over r equals m sine theta over cosine m cosine theta. M's cancel out. Sine over cosine equals tangent of phi. I think I said theta, but it's phi. So then rearranging this, we get phi equals arctan of I over r. Right. So there's our I and r, and our m and theta. Now this is just a trig rule, so we can simplify that to be just sine of omega t plus phi. Right, and so now from this, what we can see is we have some sine value, and we have our a times our magnitude. If this is greater than 1, then while this is at a phase shift of negative 180, the system will go unstable, and yeah, that's what I will be showing here in just a moment. Right, so here I am for the second part of part A. So I'm going to explain briefly why a magnitude of greater than 1 at a phase change of negative 180 degrees is bad, right? Why that causes instability. So we imagine we have some set point going in. It goes through our KC, right? Our gain and our transfer function here. And it goes out, and we have some value y. And then it comes back, right? So we're just having our regular control loop here. This y set point, right? Let's say we have a step change, right? This can be broken down into a series of sine waves, through like a Fourier transform. So we can say, let's say we have some sine wave going in here, right? So just one of these waves, that's all we are concerned with. Then we have we have our wave here, right? Some amplitude A, right? And A is like that. And then we bring in our y here, right? Y goes in as another sine wave. And let's just say this is slightly bigger, right? So this is slightly bigger. If we break it down, right? This, right, in our little controller here, in our, we subtract our y from our y set point. So this suddenly becomes additive, right? If I can draw that better, right? So something like this, right? Where now we have this y is going to be greater, right? And it's going to add to it. And so even if we take off this value here, right? Right, even if we shut off our set point, we have a greater y value going in to the same controller, which will increase it again, right? And again, and again, and again, uh, which of course just means we are going to get massive oscillations for that, specific sine wave. Of course, it could also be more, but it's just going to go completely unstable uh, in this scenario. So, that'll be all for part A. Now I'll be moving on to part B.